Hey, welcome back to Calc 2. In this video lecture, we're going to take a look at another series test, another test for convergence of infinite series. It's called the alternating series test. This video lecture, I hope, will be a little bit shorter because there's just one test in here, the alternating series test. I want to tell you what it is. I won't be proving it in this video lecture. You can ask me about it in class if you want to, but I just want to state it, and then I want to illustrate how you use it with about 4 examples. Okay. So in this instance, I couldn't motivate this subject any better than your author does. So I just kind of clipped a little section out of your book, and let's just take a look at it here. So what the author is saying is that most of our tests so far, with the exception of like the geometric series test, have required that we be considering series with positive terms. Yeah, so the comparison test, the limit comparison test, the integral test, it all required that the terms be greater than 0. So now we're going to learn a little bit about how to deal with series whose terms are not always positive, but half of them are. So in particular, we're going to look at these so-called alternating series. So the word alternating here is referring to the signs in each term. They're either switching like this, plus, minus, plus, minus, plus, or they start with a minus, minus, plus, minus, plus. But in any case, they're alternating. Yeah. In these two examples, the terms without the signs are 1 over n and n over n plus 1. And then you guys remember that powers of -1 are how you get the signs to alternate. So here the author is starting both these sums at 1. So if you put the exponent n minus 1 or n plus 1 up there, then you'll start with a plus. If you put the exponent n, you'll start with a minus. Okay, so these things all have the form. The terms of the series look like some plus or minus sign times a number that's positive. Terms of the series, plus or minus sign, term that is positive. So the bn's are just the absolute value of the an's, and they're positive numbers. All right, let's look at what the alternating series test says. The alternating series test says if you're given one of these alternating series, if you ignore the signs, the b's are positive. The plus and minus pattern is put in there by the powers of -1. So you have b1 minus b2 plus b3, or it could start with a minus sign. It doesn't matter, but they have to alternate in terms. Then you have to check two things. One is that the b's are decreasing. So as you look out in the sequence, B2 is less than B1 and B3 is less than B2, or at least less than or equal to it. So the terms have to decrease, and for that matter, they have to decrease to 0. Okay, so that's what we're going to have to check in each one of these examples. And I actually usually check them, to be quite honest, in the other order. I usually look at the terms going to 0, because if they don't, then the divergence test tells me to work no further. And then I worry about whether they're decreasing. Sometimes you can just see that. Sometimes you can see it. Sometimes you're going to need to use some differential calculus that I'll remind you of how that works. Because remember, in Calc 1, the first derivative of a function of a continuous variable can tell you whether a function is decreasing or not, yeah, when the first derivative is negative. Okay, let's look at an example. My usual disclaimer here. Every example I'm going to talk about below, the question is, does the series converge or diverge? All right, I'm not going to write that over and over again. Here's our first example. This thing is called the alternating harmonic series. Because if you ignore the plus and minus signs, it's just the series 1, 1/2, plus 1/2, plus 1/3, plus 1/4. That's the harmonic series. It's known to diverge. Integral test shows that, but this is the alternating harmonic series. So just to match the notation, I'm not saying you have to do this, but you can still see that theorem up there. So here our b sub n is just 1 over n. B sub n is just 1 over n. And it's clear that those terms are decreasing, right? 1 is bigger than or equal to 1/2, which is bigger than or equal to 1/3, which is bigger than or equal to, and so on. All right. If you want, I can use this as a real quick example of how to use differential calculus to show that that's decreasing. So these terms are decreasing. That's what this first condition up here is asking you to check, that the terms decrease. Here's a differential calculus way of showing that. It's trivial in this example, but you just take a look at your corresponding function, right? In this case, the corresponding function would be 1 over x, just like we do for the integral test. And I take its derivative. The derivative of 1 over x is negative 1 over x squared, which is less than 0 for all x, actually, but in particular, for all x at least 1. I'm starting at 1 because that's where my counter would start. So if a function's derivative is negative, that function is decreasing. Okay? So that's a differential calculus method to establish that hypothesis that your terms are decreasing. What was the second hypothesis, or the thing we have to check is that the limits go to 0. Okay, well, that's trivial in this example. The limit as n goes to infinity of 1 over n is certainly 0. We've computed it a dozen times. So the alternating series, the alternating harmonic series, the series whose terms are negative 1 to the n minus 1 over n, as n goes from 1 to infinity, converges by the alternating series test. Okay, so the harmonic series itself diverges, but the alternating harmonic series converges. I said I wasn't going to give a proof of this, but while we're talking about it, let me just give you kind of a proof that the alternating harmonic series should converge. Because if you think about its partial sums, its first partial sum is 1. Yeah, and then we take away a half. Okay, 1 take away a half is a half, and then we add something, but what we add is less than what we took away. Yeah, so we start with 1, you take away a half, and then you add a little bit less than that. And then you take something else away, but what you take away is a little bit less than what you just added. Yeah. And then you add something a little smaller than that, but you take away something a little smaller than that. It's sort of intuitive that you're going to converge on something, because each time you increment, you either add a little bit, but it's less than what you just took away, or you take away a little bit, but it's less than what you just added. So you can kind of intuitively think like, yeah, that should zoom in on some value. What is the value? That's a different question. I'm not trying to answer the question what the alternating harmonic series sums to. I just know that it sums. Maybe you can ask me in an online class or office hour if we could figure out what it sums to. Okay, let's look at a second example. You'll have to stop the video and scroll back up or look in your book, because you have to have that test in front of your eyes here. But so in this second example, I want to know, does this series converge or diverge? My bn's this time are 3n plus 1 over 4n minus 1. And although I didn't take my own advice in the first example, I am going to here. I'm going to take a look at the limit first. I'm going to take a look at the limit of 3n over 4n minus 1, because that's equal to 3/4. That's not 0. All right, so these terms are not approaching 0. So in some sense, the alternating series test doesn't apply, because we haven't met its hypothesis. The alternating series test, we can only use it when these terms go to 0, so it does not apply. We haven't met the hypothesis, but can you finish the sentence here? This series, although I ignored the plus and minus signs, this series, its terms rather, if you throw in the alternating signs, if the terms themselves without the signs are approaching 3/4, then with the signs, that this limit is not going to exist. It's going to be trying to be 3/4 and minus 3/4. And if that limit doesn't exist, we can say that the series, I'm being lazy here. Let me not be so lazy, but I don't want to write it again. My handwriting is degenerating and I'm getting tired. This series diverges. You know why? It's not by the alternating series test. The limit of its terms doesn't go to 0. It just diverges by the divergence test. Okay, so that's why I kind of like to check this limit first. That limit's not 0, don't proceed. Series diverges by the divergence test. You don't have to worry about checking whether something is decreasing. Why bother doing that? The series diverges, we know it. Cool. Let's look at a third example. Okay, so this time, what are our b sub n's? Our b sub n's are n squared over 1 plus n cubed. Yeah, I'm going to be a little bit, well, yeah, here, let me do it. So I'll check my limit, follow my own advice. So n squared over 1 plus n cubed. Are you sequence limits experts yet, champions? Can you say without me saying it what that limit is? Pause, put in some details if you need to, but I'm just going to say it. It's quadratic over cubic. That limit's 0. All right. So I do need to proceed here. These terms are going to 0. So I'm almost ready to say this series converges by the alternating series test, but what else do we need to check? We have to check one more condition. We have to check that this sequence is decreasing. And that's maybe not so obvious. You know, if you write out some of the terms of that sequence, the first term is a half, 1 over 1 plus 1. The second term is 4 over 1 plus 8, or 4/9. Yeah, okay, well, 4/9 is a little bit less than a half. It's true, but we need to guarantee ourselves that those things keep getting smaller. Okay, so that's the question: is bn plus 1 less than or equal to bn for all n? The answer to that question has to be yes for the alternating series test to apply. So here is how you can answer that. You look at the corresponding function. Excuse me, x squared over 1 plus x cubed. Just changing the n to a continuous. And then you take the derivative of that function. I'm going to omit the details here. You would take the derivative of that function, with the quotient rule. And after you do that and simplify it, I hope you're going to stop this video and check this, because this is something that I need you to be able to do. But you can work out that that derivative is going to be, when it's all said and done, and this probably, at least the denominator looks right, yeah, from the quotient rule, it looks like that. Okay, so in looking at this thing, what's going to be its sign? Yeah, I'm always, with these things, I'm just interested in x greater than or equal to 1, because I'm thinking about x, the whole number, n equals 1, 2, 3, and so on. So if x is greater than or equal to 1, that's a positive number. This thing down here is a positive number. So it's this factor, the 2 minus x cubed. Well, if x is bigger than the cube root of 2, then that thing is negative. So the cube root of 2 is a little bit bigger than 1, but still, eventually, as long as eventually, for any x greater than or equal to cube root of 2, this derivative is negative. So what does that mean? That means that bn plus 1 is less than or equal to bn. Well, for n bigger than the cube root of 2 anyway, and that's good enough. So this series, I'm just going to write the series, it's this one. This series converges by the alternating series test. Yeah, because it has, ignoring the signs, its positive terms decrease to 0. The alternating series test says if you have alternating signs and the terms ignoring them decrease to 0, the series converges. So it's actually a pretty easy test to use. The hardest part is kind of checking this hypothesis. I hope that you're going to take the chance to remind yourself of the quotient rule here. Stop this video, because this one's not going to be that long. I just got one more example. I want to know, does this series converge or diverge? Okay, so in this case, our b sub n's are n times e to the minus n, or maybe you like to think of that as n over e to the n. I hope that you have enough experience with these limits that you can tell me what happens to n over e to the n. If you want, you can treat it as a continuous thing and use L'Hopital's rule, but exponentials grow faster than any polynomial. That limit is 0. So the question is bn plus 1 less than or equal to bn? And I mean eventually. I mean, for some value of n and they're out. I don't care if there's a finite number of exceptions at the beginning. So let's try the differential calculus, the corresponding function. Do you know what I mean by that? Can you write it down before me? The corresponding function is x times e to the minus x. Yeah. So here, I'll differentiate this one with you. It's the product rule. The derivative of x times e to the minus x is, well, it's the derivative of x. It's 1 times e to the minus x plus x times the derivative of e to the minus x. So if you do a little bit of algebra on that, if you factor out your e to the minus x, it looks like it's e to the minus x times 1 minus x. And that quantity is negative. Remember, e to the minus x is always positive. So that quantity is negative as long as x is bigger than 1. Okay, so good. So what does that mean? That means that bn plus 1 will be less than or equal to bn. Our function is decreasing. It's got a negative derivative on for x bigger than 1. So our series converges by the alternating series test. All right, there's 4 examples. I got 4 more for you in the activity, and then I think I asked you to do 10 of them in the homework that you can check on Slader or talk to me about. So if you do those 14 problems using the alternating series test, it'll remind you about some of your differentiation, get you used to this notation, and make you proficient in using this test. All right, I will see you in the next section.